read the journal very well. It's read enough. It's false hope if you think you're going to be preventing yourself from getting sick with that. This level, it doesn't stop the virus. It does catch things that when you sneeze and prevent that stuff. Okay. We're going to do this, it's open circuit stuff. So first thing on the Smith chart, if you have a Smith chart, it's useful to work these things with me. And this is a shunt stuff, not series. It's important. Shunt implies parallel. Everybody with me? Anytime you hear shunt, we're working the admittance domain. You all got that. Shunt, admittance, if it's anything to do with a series connection, or they'll say series connected stuff, then you work in the impeach domain. So here's the Smith chart, my Smith chart. Now we start by just finding the normalized load impedance, which is going to be 70 plus J110 over 50, right? And so what is that? About 1 point, that's going to be 1.4, right?
1.4 plus J 2.2.
All right. So I know that these are my markers that I use. This is J1 here, right here, and this is a 1 circle. So if I'm looking at 1.4, it's going to be a circle about here. You may have to estimate it on your Smith charts. So that'll be the R 1.4 circle, about. Can you all see that, class? Just making sure everybody knows how to locate the first point. You have to be able to do this to go on. Clear on that one? Now, after that, the next thing you have to do is locate this J2.2. So if this is J1, J2.2, I'm guessing is about there, and it'll be a trajectory like this. Just make sure y'all can see this. Pick your Smith charts out, I'll give you a second. Locate this first point. The intersection of those two lines is your first point. It's ZL, which is 1.4 plus J2.2. Can you all see that? All right, now I hope you brought your compass and straight edge. So the next point, remember, it's going to be a shunt stub connection, so we're going to go right into the admittance domain. Follow me, class? Everybody with me? Admittance. So if you have your compass, just take it out to this point from the center of the circle, and then draw a circle of constant radius here, which is a constant magnitude reflection coefficient. It'll go like this, as such. Just draw that out. You were in my office, and there was that software I was using, whatever it was, EMAG.com, that I literally took the pictures of it and pasted it up there. I'm going to send this software link to everybody. It'll allow you have to enable Java, and you can only do this, use this software with Explorer. So there's some tricks to this. He helped me with his phone to make sure I could work it, but it'll allow you to solve any possible problem and give you the exact solution you can compare to yours. If you have questions, it's nice to have the right answer and see the right method for any possible problem. So, can you send me a message or somebody to please send the software link? Sure. I want to make sure I do this. That's the first one. Now, where is YL? It's going to be at the opposite point, right? YL technically is 1 over ZL, and it's right here. That's point 2. Everybody got that? And by the way, where are the quizzes right now? Go around. Give it to him. And you can take them all up front. Just get yours and leave a pile up here in the front, or wherever you want to sit. You all with me on this, class? Now, YL is 1 over ZL, and I'm not sure what it is, but you might as well just tell me right here. What is YL? 1 over ZL. Just, you can either look at it or you can use your calculator. Calculator is easier.
0.206 minus 0.324, or J324.
That's fine. It's here, right? Now take your straight edge and just throw a line right through here. And then on the outer edge here, on the wavelength towards generator portion, tell me where that intersects there. I need a mile marker there, so I can move that. 0.446. I have 0.446, anybody second that? Remember, this is 0.5, right? 0.446, people?
0.448.
448?
I think I'm 0.448.
Something like that.
Somewhere 0.448, again, we'll go there. 0.448 lambda. Now that's the mile marker that tells you where you are at the load and the admittance domain. All with me on this one? I want to make sure. I'm going to give you time to play around with the Smith chart. I'm not trying to hurry this along. And if you have a question, don't think it's a dumb question. Ask us. And work together as much as possible. You'll help each other. Trust me. There's something they see that you don't, something you see they don't. It really is helpful for people to interact. Y'all get this, class? Now, remember, we're going to do this, and I should draw it over here. We're going to do this with an open circuit stub. So here's my ZL, right here. Here's my Z0. I've come in, I actually have a normalized Y of 0.26, 0.206, minus J of 0.324. Now I'm going to start moving this way. All right? I'm moving this way for an attachment point. And as I'm moving that way, what I'm moving is on this circle, I'm moving wavelengths towards generator. Are you with me? And I'm going to be moving on this inner circle. I mean, this is actually the positions, the possible values for the load or for the input admittance as I move closer or further away from the load. Y'all with me? Now there's a caveat. There's 2 points you automatically mark up. Wherever this circle intersects the one circle, this is the first, and this would be the second. Y'all see those? Just mark them right now. We'll talk about which one to select in a second. Y'all, everybody with me on that? Now, there is going to be a condition or a limitation that's put on us by the statement of the problem. He says use an open circuit stub, which I'll get to in a second, but then there's a qualifier. What does he say next?
Choose a solution that minimizes the length of the through line.
The through line.
Yes.
Interesting. That person's being sneaky. All right. So now for the stub itself, I'm going to do this with the stub. It's going to be an open circuit stub, right? Now we're going to work in the admittance domain. Please, you all follow me. Anytime we're in parallel, we're in the admittance domain. So now I go through this, but I go through this the same way I always do. I start with the load impedance, which is infinite, right? If it's open circuit, there's no load, it's infinite. Y'all follow me, class. Please make sure in your head this is absolutely straight. Now I go and I normalize it. If it's infinity divided by Z0, it's still infinity. Y'all with me? Now I go to the admittance domain. 1 over infinity is 0. That means at this point right here on the Smith chart, I enter at 0. Y'all with me? So I'm going to try to draw my mini Smith chart here. And if you look, I'll go right through the axis here. This point right here is infinite, and this point is 0. Now, I know this point corresponds to the beginning, or the 0 marker, 0 mile marker, and this is the 0.25 mile marker. But right now I'm talking about the value of the impedance. It's J0. Do y'all see this? It's right on the rim. There's no real component. Now they don't want the length that minimizes this, right? They want the length, they want the stub value that minimizes the through line. Y'all hear me on this? So what they're talking about is they want the distance from the load to the attachment point to be the minimal distance. Y'all hear me? It's in parallel though, remember. So here's where we came in at, and I'm going back to that. I'm right here, right? Y'all with me? If I move from here to this point right here, That's the shortest distance possible to get to the 1 plus or minus jx, right? So that will be the position that I'm going to put the shunt on. Everybody with me on that? Now we get the value of this. I'm going to just say this. I know the real part's 1, but what is the imaginary part at this point? This is going to be how far we move in the value. It's going to be 1 plus j what?
1.85?
I want to make sure everybody sees this. I've got a 1.85. Take a look. You're going to get variance. It's just inevitable.
1.9. I got
1.9, 1.85.
I got 185.
All right, and you will see some slop depending on how accurate you drew the circle and, you know, more or less how sharp
Yeah,
your
it's
pencil
1.9.
point is. All right, 1.9 is good for this discussion. Got it? All right, now how far do we move? Well, next thing I've got to find is this mile marker here, right? Blank wavelength towards generator. What do you get for that? Now please, this is the outer circle. Look careful. And if you need to use glasses or magnifying glass, then please get them. Because I know with my eyes, just looking, if I don't have glasses, I'm going to have a hard time. I'll probably mess that up. What you do? 0.184. Did you get about that? 0.1. How many got that? 0.184. 84 lambda, right? So now we're going to figure this distance out. We started down here, right? We ended up there. So what we do is take the point we landed at, which is 0.184. So this distance here, and I'll call it B through, is equal to 0.184 lambda minus 0.448. But what do I have to do? Because I know it's negative, right? I know that value is going to be negative, isn't it? That's the mile marker I landed at, minus the mile marker I started at, is how far I traveled. But if it's negative, what do we always do?
Flip to the positive.
Add exactly 0.5, right? 0.5 lambda. Correct, class? So you just add plus 0.5 to it. Add 0.5. And what do you get? I hope I'm being clear. Sometimes there's very small subtleties that can be
0.236?
0.236, guys? Is that right? All right, so it's 0.236 lambda. That's just shy of a half or quarter wavelength, just shy of a quarter wavelength. 0.25 would be a quarter, right? All right, that means we've got this distance here. Now we need, here's where we're going to connect our open circuit stub. Now we need the stub length. Okay, so back to this thing. We're here, and I made the case, if it's an open circuit stub, then the impedance is infinite, the normalized impedance is infinite. The admittance, the normalized admittance is 0, correct, class? How far do I have to move? Here's where I'm going to start, right? I'll do it in this one. I'm going to start right here, right? Y'all follow me? That's 0. How far do I have to move, class?
1.9?
Until J is, now think, this is positive J 1.9. What do we want to land on? Minus J 1.9. Where is that? Well, it's at least a quarter wavelength, right? Until we get a quarter wavelength around, we're not getting negative values of J, right? Everybody? Now you're going to keep going until you hit, I'm going to guess it's about here, and you're going to see it'll be J 1.9, and it's got a minus there, but I don't think it's indicated in all spin charts. So then shoot a line through there. Make sure you go from the center right to the value where that trajectory, that 1.9 trajectory intersects here. You've got to go straight through here. And then you're going to look here and you're going to see something wavelengths towards generator. You'll have to give me that value.
0.315.
Say that again?
0.315.
Anybody confirm that? 0.315? Okay.
No, it's.
I got 0.325.
Three. All right, we got 1525. Keep going.
Yeah,
Look.
325, 327,
325.
it's all in there.
All right, now here's where the problem lies, in my opinion.
Previous point was the R1.
Take that straight edge, and this is the truth, this is how you mess up. You don't want to go right with a straight edge, right through the point where the J intersects the edge there. And don't follow this curve this way, go straight out, and tell me what you read.
0.334.
0.334? Take a careful look. What do you get?
I think we're all getting 315-ish, 314.
All right, then I'm gonna see if it's a Smith chart problem.
315 is on the R=1 circle.
Yeah.
That's 3.315 is the location of the J negative, J minus, or
Yeah.
1 minus JX on the R=1 circle.
No, I don't care about that. I care about this. I
Right.
wanna know just the J.
That's 0.325. If you go off the R=1
Yeah,
circle.
hold on, let's, class, hear me, all right? I don't care about this point right here, at all, all right? We're not talking about this, we're gonna use that point, aren't we? That's where we're landing, that's the short distance, please hear me. Now, go over here, this is a different Smith chart. I'm only gonna be moving on the rim here. This has to do with the stub, everybody got me? Now, please, everybody take a look, if you go all the way around here, where J 1.9 is here, shoot a line straight through here, what do you read there?
0.325?
325, 326?
325, 326.
All right. 0.325 length, I'm just gonna go with that. How many see that? Y'all see it? Sir, do you see it over here? Do you see it? What's that?
They're going through the actual point at the R=1 circle instead of going on the outside.
Who is?
That's where they're getting that 3.5.
Well, no, you move right, look, this is the point we landed at here, right?
Right.
All right, what we wanna do is add something in parallel that gets rid of this. Y'all with me?
Right.
Don't worry about that point. Forget that point. You want this point, just J, right on the rim. Y'all see it? I'm gonna come down there and make sure. Starting to concern me.
Yeah. So you got 0.32 roughly.
I got 327, but that last digit's an
Is he saying you literally just go through the wall?
No,
R=1?
you don't go through this. The only time you use, you just.
So how you use the R circle for this position, right? You want to set one parallel to go to the negative one.
Yeah, the R=1 circle.
Now you're looking down the longer at this R circle, you're looking at this 1.9 value. That's why line straight out.
At the R=1 positive, go to negative. J
Because that's what it is.
Right,
Yeah.
so positive 1.9 negative. So
That's like the distance.
That's the impedance rate speed.
Yeah.
So we need to get it, even with positive points, we need to get a negative J.
Overall distance is apparently 1.9.
So don't go to this point right here, because this point is actually like J.
So do we just go to the? Sorry, no.
Yeah, so we start over
Yeah,
here.
yeah, that's very
The
important.
imaginary value says 1.
That's all this is. That makes sense. Thanks. So it's literally the same thing as 1.9 up here, you just go to the imaginary down here. 1.9.
Yeah, so then positive, negative.
Yeah.
But yeah, you can start drawing different lines.
There's no way to I was worried, I was sitting there. Put this in here. Screen.
I'm sorry, no, actually, you are right. You are right, my bad.
Yeah, I got it.
You got it?
They're great when they're new.
Okay. All right, now I'm gonna tell you, I'm gonna level with you with this. I have taught this course many times. This is the biggest common mistake. You will look at the original Smith chart that you charted the 2 points, and you'll take that point because it's the conjugate value, the J 1.8 you want to get rid of, or 1.9, and you go there and you get the wrong answer. I'm just telling you, I know this. You have to be focused when you do it. And it's easy mistakes like this that cost you big points. Okay. Back to this thing. We got a value of 0.325, correct, guys?
Yes.
All right, we started at 0. This is a no-brainer. The distance that stub length is 0.325. You got me? Because it's 0.325 minus 0, correct? I'm going to see this. Everybody? Okay. So that means this stub length is 0.325 lambda. Now, what does the Whitworth's book have? You asked me about it.
0.328.
328?
We're definitely wrong.
You're gonna get that kind of variation. It's inevitable, you cannot avoid it. You're gonna always get some variation. Now, the tool I send you will give you an exact value, but I'm gonna level with you about one thing, and this is so important. Nothing that is fabricated is exactly what it says it is. There's imperfections in the dielectric constant, in the line material used, and the whole idea is this. You try to minimize the amount of slop and error, but no matter what you do, you can't. And here's the other thing. This is for one single frequency. Only one frequency. As the frequency goes up, the wavelength shortens and the line length shortens. Then you're not matching exactly. When you're transmitting, you don't transmit just a single frequency, usually. You have a modulation index where there'll be a bandwidth. And so there'll be variance in there for the amount of matching. So you just gotta be aware of all these things. Okay. That's a good problem because it highlights some of the concerns I have when you're doing open circuit, which I hate, and then all of a sudden the constraint is not minimizing the length of the stub, but minimizing the length from the load to the connection point. You see this? And you have to be able to do this, design things based on the constraints. And I have a question for you, and I want you to think about that answer and record it, because suppose I gave you this problem. Now hear me. I'm going to give you the same exact problem, same load and everything, but there's a different constraint. Now, instead of an open circuit stub, I'm going to use a short circuit. Hear me? Exact same problem, only now I want to minimize the length of the through line, only using a short circuit stub. Hear me? Does this point change where I'm going to attach it? Class?
No.
Not one bit. If you're minimizing that length, that is the minimum length period. Now, if it's a short circuit stub, where do we start? Right here, right? And now our short circuit stub length is going to be much less, right? Y'all follow me on that? It's going to be a quarter wavelength less. How many see that? Make sure you see that in your mind. I can go through the constraints. I could say, I want you to minimize the length of the open circuit stub. Now, the whole idea is this. That stub is either going to have a plus or minus J limit, right? If you come in with an open circuit stub, the first thing is a plus J. With me on that, class? Everybody see that? This is a short, just any incremental length to that line, it's a plus J. That means for this to be minimum, the point you would select would have a minus J here that you're going to get rid of. Y'all follow me on that rationale? Now, if I said, and I can go, I'm going through this in my mind, I could come up with about 3 or 4 other things, but the constraints are things that you think about, and think about the fundamental thing you have to deal with. If they want the minimal length of the stub, then you always got to figure, if it's short circuit, right? Short circuit, if it's a short circuit stub in parallel, the values of Y are negative J, right? That means we want our attachment point to be 1 plus J, whatever that imaginary part is. Got me on that? If it's an open circuit over here and we want it minimum, if we come in over here, then we want our attachment point to be here where it's a minus J. And just be aware of these things and work through it in your mind. Then you won't have any problems. I promise you. I've got a question for you, all right? Now hear me and just think and then answer. After this stub is connected, once I connect that stub right here, and I connect, right? what is the input impedance over here? What is Z in? I'm on this side. What would it be? After the stub is connected, so I'm on this side.
Zero.
It's gotta be Z naught, right? Because the reflection coefficient is 0, right? The whole idea of connecting this stub is it'll make everything on that side of the stub connection look like Z naught, so you get no reflected wave. That's the idea. Your reflection coefficient is 0, okay? Now, over on this side, what is the reflection coefficient?
0.
0. What would the standing wave ratio be?
1.
1, all right? I'm just trying to make sure you're clear, yep, on that.
One question I do have is, as we move, so if the line is lossless, I can understand how for stub, you change the J component of the impedance. As we move away from the load, we're changing, and we move towards that R equals 1 circle, we're changing the Buell component of the impedance. How
Yeah,
does
well-
changing the line length do that?
Yeah, well, the thing is, remember, as we move away from here, okay, we're moving on a circle of constant reflection coefficient magnitude, right? The real part and the imaginary part are changing simultaneously. So when I'm moving on this arc, if I'm here, if I'm in the admittance domain, the values are changing continually, but the radial distance is the constant. That's the thing. So don't worry about it. The values are going to change, but see, that reflection coefficient is going to have the same magnitude always. So standing wave ratio on this section will always be the same, and it will not be 1. It's, the reflection coefficient will be a constant. Got me on that, class? All right. By the way, what is? Tell me on this. What's the reflection coefficient on this line with an open circuit?
Is it 1 or 100%?
It's 1. It's either plus or minus 1 on any stub. It's never going to be 0.5. It's always either it's minus or plus 1. What's the standing wave ratio? Infinity, right? 1 plus the magnitude of the reflection coefficient over 1 minus. But that means that on this thing there will be absolute voltage nulls, and then there will be voltage points where the voltage doubles. But I don't want to spend a whole lot of time on some of these subtleties. It's important to be aware of this. On a stub, everything's reflected. There's nothing absorbed. It doesn't absorb energy. Okay. Any other questions? That was a good question. Yeah.
Part 2 of this problem says, suppose that the load turns out to be 40 plus J 100 ohms.
Okay.
And wants us to determine the reflection coefficient, like
After, with the stub. Great problem.
40.
All right, what we're going to do, ready? We're going to leave the stub intact. All right, and now what we're going to do is replace that load. So what I'm going to do is, I'm going to leave these values out here. I'm going to erase that thing, and I'll try to explain this part. This is the good part, because this is stuff that now you have to know what you're doing. All right. So everything's, this is the length of the stub. All right. We're saying that stays the same, the length of the stub stays the same, the connection point stays the same. We're changing this. And what was the new value?
40 plus J 100 ohms.
All right. Z naught is still 50, right?
Yes, sir.
So that means my normalized load impedance is going to be 0.8 plus J2, correct?
Yes.
All right, with me? Now, I'm just going to try to draw this up here as best I can. So we've got 0.8 plus J.2. 0.8 is going to be about this circle. If you look, that'll be about R equals 0.8. And then J2 is right about here. So if you follow this in, this should be your first point, ZL, which is equal to 0.8 plus J2. Can you all see that? Now remember, we attach that shunt stub in parallel, correct, class? Just keep that in mind. Okay. Now, after that, you take this and you take your compass. Actually, you can do it this, yeah, you're gonna need a compass. No, you're not actually, I don't think. You're gonna need to get the reflected point here, YL, which is, or conjugate point, which is 1 over ZL. And if you can tell me what that is, just take 1 over 0.8 plus J.2. I can't do that, Mike.
0.172 minus 0.43.
Minus J 0.43.
Yes.
All right, now you need to do one thing. Right here, you need to get me wavelengths towards generator. You give me that mile marker. This is a good problem. I'm so glad you asked this one. Because it's really, it's spotlighting all the areas that people usually get confused on.
Like 0.435.
0.435, can you all see it? How many got about that?
0.43? Yeah, am I getting, is that low? That's high. What did you get?
Remember, it's wavelengths towards generator. Go ahead, Miss. 436? 436?
Yeah.
435, something about that? We'll go about 0.435 lambda. Let me make that a little larger. And that's wavelength storage generator. Now, y'all with me?
He had an old ZL.
No, I got new one.
Oh, everybody with me on this? Now, how far are we gonna move from there?
It's J2.
Well, we're gonna move,
Yeah.
how far? Y'all see that? I mean, do you all see he didn't change the length from the distance where the stub's attached. So now we've got to move 0.236 lambda. Y'all with me? That's just shy of a quarter. So now we're gonna go ahead and we'll basically come to a new mile marker. I'm not sure exactly where it is, but it's about like here. And we'll get this wavelengths towards generator, but let me just tell you this, that new mile marker that I'll just call alpha, if I take alpha minus this, minus 0.435, right? If I take that, that has got to be this distance, which is 0.236. Right, I'm solving for alpha, but I'm making a comment here. Are you all with me on what I'm doing? I know before, position I land at that I don't know, that's alpha. I'm just giving it a value. Minus the position I started has to be the distance, right, in wavelengths. But I know this is going to be negative, right, because I'm over here. So I add half a wavelength. Y'all with me? So right off the bat, I add half a wavelength to this. And now give me the value of alpha. So alpha is going to be 0.236 plus 0.435 minus 0.5, and whatever that is, that's the position we're going to land.
0.17.
0.17? 017?
1.17.
Okay. So we're going to move to 0.17 lambda, and that should be this point right here. Want to make sure y'all see it. That's where we're going to stop. Got it? Y'all see it?
Yeah.
Now, you should take your compass now and just do this. I mean, this is nice. But you've got to give me this value right here, and that would be in Y. Tell me what that value is.
0.6.
Take a careful look at this. This is where we moved to. We started here, right? We were at the load. We're moving on a different trajectory or a different radius distance. We moved to here, and what do you get for this again?
Yeah, 0.6 plus 1.7 J.
Y'all get that? I want you to take a careful look, make sure it's right. Can you see this? All right, make sure you see this and you don't have any question about how that value is obtained. You good with that? I'm waiting for everybody. Take your time, just be sure you're clear. Does anybody not see that or need a little, assistance, somebody to point you in the right direction? Do you see it, sir? You good with that? You good? Everybody here, miss? Okay. If you all see it now, what do I do now? Now I got the normalized value of y at the point the stub was connected though, right? And what was the value of the stub's admittance? What did we get? Minus J 1.9, right? Isn't that right?
Yeah.
So now, what we're gonna do when we add these two together, this admittance right here was minus J 1.9. We're gonna add it to that value. So at the point where the stub was connected, the Y new value would be equal to Y of the stub, that's the old one, plus 0.6 plus J 1.7. And the stub's value was minus J 1.9 plus J 1.7 plus 0.6. So that means I've got 0.6 minus J 0.2 as my new value of the normalized admittance right at the point the stub connects. Can you all see that? I want to make sure you can see it. I just added the stub value from before to the new value of Y that we got. You good with that?
Yep.
All right. Now, he asked for what? The reflection coefficient?
Yes.
Well, now here's how we go about that. That's the value that I'm going to see from here over. Instead of seeing just 1 as the normalized, now my normalized admittance has a real and imaginary part, correct? So I want you to think about the definition of reflection coefficient. I'm going to take you through it. Remember, reflection coefficient, you don't need to write this down. I just want to make mention of this. Is Z that I'm going into, Z load or Z whatever that is, minus Z naught over ZL plus Z naught, correct? Now, if I divide by Z naught, top and bottom, I get simply what? I get normalized ZL minus 1 over normalized ZL plus 1, correct? Y'all follow me? Now, ZL is 1 over YL, isn't it? Y'all agree with that?
Yeah.
So just listen to me. You don't have to do it this way exactly, but it sometimes really helps to think of it. All right, now I'm going to put ZL as 1 over YL. Anybody take a guess at what I might do next? I think some of you see it. Multiply top and bottom by YL. How many see that, right? When I do that, what do I get? YL, right? Minus 1 over YL plus 1 is the reflection coefficient. Do I have YL at that point where they're connected? Right? Sure. At this point, from here on over, that's what it is. It's just the additive value of this plus the value of, from the load, the value of the normalized admittance from the load. Y'all with me? Yeah.
Would it be 1 minus YL and not YL minus 1?
Oh, you're right. So sorry. You're absolutely right. 1 minus Y. I'm so sorry. Thank you for forgotten. It would have been negative value. Thank you so much. Yeah, that's right. All right, now, if that's 1 minus YL over YL plus 1, you got the value of YL right there, right? That Y new. Y'all follow me? I'm calling it L, but it's really Y at the point where it's connected, so the Y new. So now the reflection coefficient would be equal to 1 minus this value, which is 0.6 minus J 0.2 over 1 plus that value, 0.6 minus J 0.2. Can anybody tell me what that is? Y'all follow the rationale. Thank you for catching up. You can give it to me in real and imaginary, then give it to me in magnitude and angle. I prefer magnitude and angle, but at this point, I'm thinking.
Magnitude and angle is 0.27.
Say that, say that.
It's 0.27735. And the angle on that is 33.69.
Degrees?
Yes, sir.
Anybody else? Anybody confirm that? You got that? You got that? Anybody else? You got it?
Yeah.
All right, what's in the book? Who's got the solution?
0.28.
277, and that's slop. That's just there, your eyes, you can't help it. You all with me on this class? But that's a good problem because now, all right, we matched it for one load, we replaced that load, how bad is it? Well, that's the new reflection coefficient. Actually, that's pretty bad. All right, you're almost 25% for the value, a quarter. That means your standing wave ratio, it's over 2. That's not good. Anyway, y'all follow how it's done. I guess I should turn off the sound, but maybe we'll hear something really crazy. All right, now I got 5 more minutes. Any other questions before I get into what I was about to talk about? Let me go ahead. Today, I planned on, but this is even more important, we're doing time domain reflectometry. And I'm going to tell you guys, this will make logical sense to you, I think.
It's pretty close. Yeah, but then. Alright, well,
Is it 1 minus all that? 1 minus all I think you're right. I think it's just.
All right.
Yeah. Look at something small.
So get a new sheet of paper, turn the page, and just put down TDR, time domain reflectometry. I didn't know better. Anyway, so this is time domain reflectometry. Here's what goes on with this. We're going to start by having a battery of some value V0. And then you put a switch in front of it. Then you let the switch close at T equals 0. Now you're used to switches from back to transient transit circuits. You know, these are standard schematic models of switch. Then put in a resistor in front of it, RS. And then you're going to do something. Put 2 little circles. Then the next thing you're going to connect is a transmission line. So here, we're going to have a transmission line with a characteristic impedance of Z0. You're going to have a load over here, ZL. And you can call that 0. We're going to say the length of this line is L. That's the characteristic impedance. We're going to do something else. We're going to say the speed of light on this line, or phase velocity, is going to be the velocity of light. It doesn't have to be, but pretty much all lines are about the speed of light for transmission lines worth their salt. Now, after that, here's the deal. When I throw this switch, and just imagine this, as soon as I throw that switch, then there's going to be voltage division that happens between RS and whatever the impedance is here. You all see this? Now it's important you grasp this concept. As soon as that switch changes state from off to on or short, it doesn't know how long the transmission line is. It doesn't know anything about what's down this way. The only thing it knows is the characteristic impedance of the line right here. That should make intuitive sense. So there's gonna be a voltage pulse developed that we call V prime that's gonna propagate that way. But V prime you find equal to this voltage, and it's just found using voltage division. Z naught over Z naught plus RS. Now that should make logical sense. If we talk about voltage division of any two resistors, you take the source voltage that's across both, multiply it by the resistor you want the voltage across, and then divide by the sum of the two resistors. Should make logical sense. Now this pulse is going to propagate at the speed of light until it strikes this. And at this point, there is a reflection coefficient at the load. And that's equal to ZL, right? Z load minus Z naught over Z load plus Z naught. It's going to have some reflection coefficient. Do you all agree with that? Now, here's the thing you got to capture in your mind. Once that pulse goes down, that line has on it a voltage of V prime everywhere. All right. Now there's going to be a reflected pulse that's going to be the reflection coefficient times the incident pulse, V prime, that's going to come back this way. And as that comes back, the voltage on this line will change, and it'll be equal to the V prime plus the reflection coefficient times V prime. I'm going to show you how to diagram this, but I want to make sure at least rationally this makes sense. You send it down, bang, it hits, now some of it's coming back. Then it hits this point, and there's a reflection coefficient at the source that will be RS minus Z naught over RS plus Z naught. You all with me? Now think about it. Now that pulse came back, hits, the entire line has a value of V naught plus reflection coefficient, V prime plus V prime times reflection coefficient, up and down. It hits here, and now another pulse starts going this way. And that pulse going this way is going to be the reflection coefficient times V prime that hit it times the reflection coefficient of the source, and it starts going this way. And it's basically ricocheting back and forth. So here's a good way to actually, am I over by a minute? You can sue me. No, I better not say that. Erase that for us. I can't believe I said that. Well, the way you do this, without getting sued, is it's called a timing diagram. But here, you put the length of the line, this is going to be 0, and then they put the length here, where it is, and they just do this. You're going to just have to bear with me here. This is going to be time in this direction, going down. And what you're going to do is start with a pulse. It hits, this will be V prime. It hits, it comes this way, there's going to be something that says V prime times reflection coefficient of the load. One this way that says V prime times reflection coefficient of load, reflection coefficient of this source. Just let me finish this thought. I'm not going to hold you accountable for this with anything I do on Wednesday, but I just want you to appreciate it so you can do some more. Now, if I ask what voltage is at any point in the line, I pick a point here. You with me? Now, I said this is time. Well, the actual time, for the pulse to go from here all the way down to the line here, this distance is going to be simply the length of the line divided by the speed of light, or the velocity of propagation on the line. And they call that T, I guess, T line would be fine, but call it T line. Time it takes to go down the line would be the length of the line divided by the velocity on the line, V phase. And that should make sense to you, right? Y'all follow me? If you take velocity times time, you get length. So I've got the length, I need the time. That's this point. Down here to this point, that would be this point right here. I'm not drawing this real well. This would be simply T line. This would be T line in length, so this point would actually be 2T line. And here's the deal. If you wanted the voltage at any point in the transmission line, please just listen to this and then I'm done. Pick the point. Say it's right at the center at L over 2. And you want the voltage in the line, you go straight down and you keep going. Now remember, this axis is time. There's no voltage on the line until I hit T line over 2. Y'all follow me? Then it jumps up to this value, V prime. And it's gonna stay there until I'm down here, which would be T line. Y'all with me? Then you would have to add to it this voltage. Then you keep on going down, hit here, now I add this voltage. So what it would look like, if this is time, and this is T line, to T line, it's 0, then it hits this point. Now it goes to whatever V prime is. Keeps going, then when I hit this point, which is really gonna be, this is T line, sorry, my bad, this is actually T line over 2. And this should be T line, I'm in a hurry now. And this would be 3/2 T line. Then it's gonna stay there, then it's gonna hit this value, and now you're gonna add something, basically the reflection coefficient at the load plus 1 times V prime, and you're gonna keep doing it. Now I think you guys are smart enough, if I give you some reading, you'll figure it out. It's not that hard to understand. The trick with timing diagrams is understanding when you get this bounce diagram to draw the lane straight down and just go down here and find out where you are on the timing. We'll talk about that on Wednesday. I'm sorry I held you. I got people out there looking at me.